Welcome to the second video in section 3.5. Here we're going to do example 3.5.1 as well as the little remark that's at the bottom of the page. So in the example we are supposed to take the function z is the square root of x minus y squared and assume that x is cos of t and y is sine of t. Part A asks us to find dz dt two ways. First, by using the chain rule. The second, by substituting in x and y's functions as functions of t and applying the derivative rules for the function of a single variable. And we're supposed to check that both methods give us the same answer. So let's start with here the chain rule. So part one, we're going to find dz dt. And if we write out the expression for the chain rule, that's del z del x times dx dt plus del z del y times dy dt. Let's calculate each of those things off on the side here. Del z del x is the partial of this function with respect to x. So we take the partial derivative, 1 over 2 times the square root of x minus y squared times the derivative of the inside, which is just 1. Del z del y, partial derivative with respect to y, so we have the same 1 over 2 times the square root of x minus y squared. Now we have the derivative of the inside, which is times minus 2y. I'm not going to simplify the 2's right away because it'll make it easier to compare afterwards, although in theory we could cancel out those 2's. We also need dx dt, and if x is cos of t, the derivative of cos is minus sine t. And lastly, dy dt, derivative of sine is cos of t. Plugging these back in, we get del z del x, so 1 over 2 the root of x minus y squared times dx dt, so I'm going to put the minus sine t in the numerator, plus we have here del z del y, so minus 2y over 2 the square root of x minus y squared times dy dt, so times cos of t, which I'll put in the numerator as well. Now it's a little strange in our final answer to have x's, y's, and t's all mixed up, so let's substitute in, and we're going to have, well, we have the same denominator, so we can write this as 2 times the root of, and if we substitute in x as cos t, we'll get cos t minus sine squared t, because y is sine t, and the numerator we have minus sine t minus 2 times y is sine t cos t. Let's do this now the second way. We'll substitute in first rather than at the end, and so we will have z as a function of t is going to be, well, if we substitute in right away, we get cos t minus sine squared t, and that lets us take the derivative, so dz dt, which is z prime of t, using the chain rule for a single variable, 1 over 2 times the root of, keep the same inside function, cos t minus sine squared t, times the derivative of that inside function, so times the derivative of cos, which is minus sine t, the derivative of minus sine squared t, chain rule, minus 2 sine t cos t. And so we're supposed to compare between our answers in the first part and the second part, and we see that we actually do get the same answer both ways. What then is the geometric or ageometric interpretation of dz dt? Well, let's start by reminding ourselves x is cos t and y is sine t, so if x is cos t and y is sine t. That is a parameterization that we have seen in a previous chapter. Now it's the parametric representation, or a parametric representation, a parameterization of the unit circle. We also have seen this function, although it might not be in a form that you recognize. Z is the square root of x minus y squared. That is, well, if we're taking the square root, we're taking the positive root, so we're taking only the top half of z squared is equal to x minus y squared, which is the same as x is y squared plus z squared. That is a quadric surface. So we have the top half of an elliptical paraboloid. And that elliptical paraboloid, if we check, is going to be along the x-axis. So let's go and draw the situation that we have. I'm going to give myself an outsized x-axis here because that's where the paraboloid is angled or facing. And so my other two axes I'll make a little bit shorter here. If we've got an elliptic paraboloid, it's actually circular, but regardless, let's draw it in. Give myself a bigger one here. So this, oops, technical difficulties. This one looks maybe something like this. And we have it coming back down to the origin and give this guy a little bit of shading here. So there is our paraboloid, just the top half of it. Now the curve, the unit circle, if we embed that in three-dimensional space, so if we take cos t, sine t, and 0, then that is the parameterization of the unit circle down in the xy plane. And so this unit circle, if we project that up onto the surface, so if we take our curve r of t and make this, well, let's be explicit, x is cos of t, y is sine of t, just like in the unit circle, but now we take those points and we put them into the function. Z is f of cos t times sine t. So obviously we can do that only in the points that are in the domain of that function, but what we are going to get is that unit circle projected up onto the surface of the paraboloid. So all of those points on the curve are going to be projected up onto that surface. So that is what the curve r of t will look like, and now we can interpret the derivative of z. dz dt is, well, it's the instantaneous rate of change of the height. So it's the instantaneous rate of change of the height of the curve r of t, height above the xy plane, as t increases. So graphically, that is what we have, or that is how we can interpret this dz dt when we've got a composition of a multivariable function and two variables of two functions of a single variable. Now something else about the chain rule, not related to the example above, but that is something that is useful and that we will use in further examples, is the idea of a tree diagram. Many people like using a tree diagram to keep track of the dependencies and the derivatives that are applicable between the different functions. So we're going to build a tree diagram for a function w of three variables, f of x, y, and z, where each of those variables is actually a function of t. So a tree diagram, we write down the dependencies. So we make a branch or a line from w to each of what are called the intermediary variables, so the x, y, and z. And each of those variables depends on t, so we draw a branch going down to the variable that it depends on t. And then on the branch, we write the type of derivative that is appropriate. Since w is a function of 3 variables, we're using partials. So del w del x, del w del y, and del w del z on those branches. Each of the lower branches is a function of a single variable, so dx, dt, dy, dt, and dz dt. And the way we use a tree diagram to remember the chain rule is by multiplying down the branches and adding up. So if I multiply down the first branch, I'm getting del w del x times dx dt plus, and then we'll multiply down the next branch. So we're going to have del w del y times dy dt plus, and lastly we'll multiply down the last branch, but of course you'd multiply down as many branches as you had, del w del z times dz dt, and there's the expression for the chain rule of a function w of 3 variables where each of the intermediate variables is a function of t. We'll see more tree diagrams in future videos.